Agent AI, it's a huge promise, right? We're talking about systems that can reason, plan, and actually do things on their own. But let's be real. There's a massive gap between a flashy demo and a production-ready system that you can actually rely on. So, in this explainer, we're going to break down the design patterns you absolutely need to bridge that gap.
So picture this. You've built an AI agent. It looks incredible in a controlled demo. It's doing everything you want it to. But the real question, the one that keeps developers up at night, is what happens when it hits the wild, the chaos of production. This is the challenge that separates a cool concept from something that delivers real-world value.
All right, so to figure out the solution, we first need to get crystal clear on the promise. I mean, what are we really talking about when we say agentic AI? Let's move way beyond the simple prompt and response model we're all used to.
At its heart, Agentic AI isn't just about answering your questions. It's about systems that proactively go after goals. They have a degree of autonomy. They can use tools, think APIs, databases, and they leverage memory to reason, learn from what's happening, and then take action.
Now, what's really interesting is how we get there. I like to think of it in 3 steps. First, you've just got the LLM itself. That's the raw brain. Then, you wrap some structure around it to create an agent. Think of this like a really capable intern. But the real magic? That happens when you orchestrate multiple agents into an agentic system. Suddenly, it's not just one intern. You've got a whole coordinated team.
And this image right here, it illustrates the idea perfectly. The LLM is your core reasoning engine. The agent adds a structured loop around it, giving it access to tools and memory. And then the agentic system lets all these specialized agents work together to solve really complex multi-step problems. You see? Each layer builds on the last, adding more capability and more scale.
Okay, so if these systems are so powerful, why aren't they just everywhere? Well, because moving from that single agent demo to a reliable production system is incredibly hard. There's a reason we call it the production wall.
And the numbers, they don't lie. According to Gartner, a staggering 52% of all AI proofs of concept fail. They never make it into production. That's more than half. So if you're struggling with this, you're not alone. This is a huge industry-wide hurdle.
And Gartner, they framed the challenge just right. There's this massive gap between a simple assistant and a true AI agent. Closing that gap means we have to learn how to build, how to govern, and ultimately how to trust these systems. So the real question becomes, what makes it so darn hard?
First, and this is probably the biggest one, is uncertainty. LLMs are not deterministic. You can give it the same prompt twice and get 2 different answers. You're working with probabilities, not predictable code, and that randomness is something you have to actively manage.
Next up, privacy. Let's face it, LLMs can be leaky sieves. They can sometimes memorize and spit out sensitive data from their training or totally mishandle private info that users give them. In any kind of enterprise setting, that's an absolute non-starter.
And finally, there's scale. A single LLM transaction is fundamentally slower and way more expensive than, say, a traditional database lookup. So, building a system that can serve millions of users, that requires a completely different way of thinking about your architecture.
Okay, so we've got the problems laid out: uncertainty, privacy, and scale. Now let's get to the good part, the solutions. We can start by taming all that randomness with some pretty clever design patterns.
The first pattern is called prompt chaining. Instead of trying to write one giant, super complex prompt, you break the task down into smaller, more manageable steps. Each agent in the chain handles one little subtask and then passes its output to the next one. It's kind of like an assembly line for AI, and it adds a ton of structure and checkpoints along the way.
Next up is the routing classifier. Here, you use one agent as a smart traffic cop. It doesn't do the heavy lifting itself. Its only job is to look at an incoming request and route it to the correct specialized agent. This makes sure the right tool is always being used for the job. Simple, but so effective.
We can also use parallelization. Why have one agent work on a problem when you can have 3? You can run multiple agents on the same task at the same time to get a result faster. Or, and this is really powerful, you can have them all vote on the best answer to improve accuracy and reliability.
And this one might be my favorite, the evaluator optimizer pattern. Here's how it works. One agent generates a response, and a second agent's entire job is to critique it and provide feedback. This creates this awesome feedback loop where the system can literally refine and improve its own work before a human ever sees it. It's like having quality control built right in.
Now, these patterns are fantastic for managing the logic, but they need to live inside a bigger, more robust system. So let's zoom out from the individual patterns and look at the overall engineering architecture. This right here, this shows the fundamental thought process of a single agent. It's in this constant cycle. It takes a prompt, it retrieves some context from its memory or a tool, it enriches the original prompt with that new info, and then it repeats. This enrichment loop is exactly how an agent builds the understanding it needs to do complex things.
So, if there's one major takeaway, it's this. LLMs are not a free lunch. They give you this incredible gift of probabilistic reasoning, but they are also stateless, they can be unreliable, and they're slow. Your job as the engineer is to build everything else around it, the memory system, the tool integrations, and the durable workflows that can handle all that uncertainty.
And that leads us right to the architectural keys you need for a production-ready system. You're going to need an event-driven design, you'll need durable workflows that don't just fail, and you absolutely have to build in clear points for a human to step in. And on top of that, robust memory and tool integration, and this is crucial, the ability to trace and debug what on earth is happening across this complex distributed system.
Which really brings us to the final question you need to be asking yourself. Are you building something that just feels cool? Building for vibes? Or are you applying these robust engineering principles to create something that is reliable, scalable, and delivers real, tangible value? Because honestly, the answer to that question will define the success of your entire project.